Welcome, fellow traveler of the mind. We meet here in the quiet expanse between sleep and wakefulness, where the velvet darkness behind your eyelids becomes a canvas for the cosmos, and the ancient patterns of stars transform into a gentle guide for the soul. This is a sanctuary not for answers, but for awe, a place to remember that you too are part of an elegant and ordered whole. When you gaze upward on a clear night and trace the familiar shape of Orion's belt or the sweeping arc of the Big Dipper, have you ever felt a quiet sense of belonging? As if those distant lights were not random, but part of a grand, silent map. A map that has guided not only ancient navigators and modern scientists, but also the human heart toward wonder for thousands of years? We are not merely stargazing tonight. We are retracing the steps of countless curious minds who looked up and dared to draw lines between the lights, who built a coordinate system not out of cold mathematics alone, but out of myth, meaning, and a deep desire to find their way home. This celestial grid is more than a tool. It is a meditation, a way of seeing that connects the intimate stories of hunters, queens, and bears written in the sky with the precise calculations that guide our telescopes and spacecraft today. It is a testament to how human imagination and reason dance together, transforming the overwhelming expanse above into a familiar landscape, a cosmic home address written in light. But first, take a soft breath and tell me, where does the sky find you tonight? Are you listening to this in a dimly lit room, wrapped in the comfort of a blanket, the glow of the screen like a private star? Or are you outdoors, perhaps on a balcony or by a window, with the actual stars shining faintly beyond the haze of modern life? However you define yourself in this moment, as a learner, a dreamer, or someone simply seeking rest, I invite you to gently release that definition. Here, you'll discover that the constellations are more than pretty patterns. They are a bridge between past and present, between story and science, between the human heart and the silent, orderly motions of the universe. They reflect a deep truth, that within apparent chaos, there is often a hidden order. Within vast distances, there can be a sense of orientation. And within the night, there is always a light to guide you. So let your breathing slow, in and out, and let the distance between you and those distant suns soften. Allow the thoughts of the day to drift away like clouds passing before the moon. Let your mind settle into a state of open, gentle awareness, ready to wander the pathways of the sky without hurry, without effort. We are about to embark on a journey not through space, but through perception, a quiet exploration of how humanity learned to navigate the infinite, and how that same act of cosmic orientation can help you find stillness, perspective, and a deep, abiding calm within. Shall we begin? We will move as slowly and gracefully as the stars themselves appear to turn, as patiently as the Earth tilts on its axis through the seasons. We'll explore how the mind finds comfort in patterns, how stories give meaning to space, and how, by learning the language of the sky, we ultimately learn to listen to the quiet, guiding wisdom within ourselves. Imagine for a moment that you are standing on a vast, open plain under a clear night sky. There are no city lights to dim the celestial spectacle above, no trees or mountains to break the perfect curved horizon that surround you. Above, the heavens are a deep, velvety black, an infinite canvas upon which a countless number of diamond-bright stars have been scattered. They seem random, a glorious chaos of light, some burning with a steady blue-white intensity, others flickering gently with a soft golden hue. The sheer number is overwhelming, and the silence is profound. In this moment, you feel both incredibly small and intimately connected to something vast and ancient. This is the same sky that is stretched above every human who has ever lived, a shared inheritance of wonder. But for astronomers, this beautiful chaos is not random at all. It is a map, a grand three-dimensional map where the stars are not just points of light, but fixed landmarks. And the patterns we see are the keys to unlocking a celestial coordinate system that allows us to navigate the unimaginable distances of space. This is the story of how humanity learned to read this map, how we turn the overwhelming spectacle of the night sky into a familiar guidebook, using the constellations not as pictures of mythic beasts, but as the foundational grid for understanding our place in the universe. The first step in this grand intellectual journey is perhaps the most instinctual: the human mind's innate desire to find patterns. Long before the invention of the telescope, before the formalized language of mathematics, our ancestors looked up and did what we all do when faced with complexity. They sought order. They connected the brightest stars into patterns, tracing shapes that reflected their world, their myths, and their fears. A group of stars became a great hunter, forever striding across the heavens with his belt of 3 bright suns. Another cluster became a mighty scorpion, its curved tail poised to strike. A ladle-shaped pattern became a bear, circling endlessly around a fixed point in the north. These were the constellations, and they served as the first chapter in humanity's celestial storybook. They were mnemonic devices, beautiful and memorable stories told in light that helped people track the passage of time, the changing of the seasons, and the rhythms of the natural world. The rising of certain constellations heralded the spring planting or the autumn harvest. The journey of others across the sky marked the long hours of the night for travelers and shepherds. This was practical astronomy, born from necessity and wonder. But as human curiosity grew, so did our ambition. It was no longer enough to simply tell stories about the stars. We wanted to measure them, to understand their movements with precision, to predict their positions, and to record the appearance of strange wandering stars, the planets, that did not follow the fixed patterns of their brethren. This required a shift from mythology to mathematics, from pattern recognition to precise measurement. The beautiful, familiar shapes of the constellations provided the perfect framework for this new endeavor. Think of it like this. If you're trying to give someone directions to a specific house in a sprawling, dark countryside, you wouldn't use abstract numbers alone. You would say, go to the old oak tree at the crossroads, then head north until you see the red barn, and it's the 3rd house on the left. The oak tree and the barn are the constellations, large, unmistakable landmarks. The specific instructions, north, 3rd on the left, are the celestial coordinates. The constellations became the anchor points, the stable backdrops against which the more subtle motions of the cosmos could be measured and understood. The ancient Greeks were among the first to formalize the system in a way that would endure for millennia. The astronomer Claudius Ptolemy, working in the 2nd century AD in Alexandria, compiled the knowledge of the ancient world into a monumental work called the Almagest. Within it, he described 48 constellations, many of which we still use today. More importantly, he laid out a coordinate system for the sky that mirrored the one used on Earth, latitude and longitude. Imagine the sky as a great hollow sphere surrounding the Earth, the celestial sphere. The Earth's equator, projected outward onto the sphere, becomes the celestial equator. The Earth's north and south poles point to the celestial north and south poles. Just as any location on Earth can be described by its latitude, its distance north or south of the equator, and its longitude, its distance east or west from the prime meridian at Greenwich, any star could be located by its celestial coordinates, declination and right ascension. Declination is its angular distance north or south of the celestial equator, measured in degrees. A star on the celestial equator has a declination of 0 degrees. The North Star, Polaris, is very close to the North Celestial Pole, so it has a declination of almost plus 90 degrees. Right ascension, however, is a little different. Instead of being measured in degrees, it is measured in hours, minutes, and seconds, reflecting the Earth's rotation. As the Earth spins, the entire celestial sphere appears to rotate around us once every 24 hours. Therefore, the sky can be divided into 24 slices, each representing 1 hour of this rotation. A star's right ascension is essentially its celestial longitude, telling you how long it will take for that point in the sky to return to the same position after the Earth has completed its spin. But how does one actually find a star's declination and right ascension? This is where the constellations become indispensable. They are the large, labeled countries on the map of the sky. Within the borders of, say, the constellation Orion, an astronomer can measure the precise position of a star relative to the constellation's brighter markers. The star Betelgeuse, Orion's bright red shoulder, has specific coordinates. So does Rigel, his brilliant blue foot. By knowing the coordinates of these bright, easily identifiable stars within each constellation, astronomers can then triangulate the positions of fainter objects, a distant nebula, a wandering comet, a newly discovered asteroid, using them as fixed reference points. The constellation provides the context, the neighborhood, while the coordinates provide the exact street address. This system allowed for the creation of the first accurate star catalogs, transforming astronomy from a qualitative practice of observation into a quantitative science of prediction and measurement. It was a quiet revolution, happening not with a bang, but with the meticulous recording of numbers against a backdrop of ancient myths, a beautiful fusion of poetry and precision that would guide sailors across oceans and astronomers across the centuries. This ancient system of celestial coordinates, anchored by the familiar patterns of the constellations, created a stable and reliable framework that served humanity for nearly 2,000 years. It was a grand clockwork mechanism, with the constellations serving as the fixed numerals on its face, marking the passage of the hours and the seasons with silent, unwavering consistency. Yet, as with all things in the cosmos, stability is an illusion seen only from a limited perspective. The great discovery that would eventually challenge this perfect geocentric model was a subtle one, a slight wobble in the positions of the stars that could only be detected through centuries of patient observation. This wobble is known as precession, and it is the first hint that our celestial coordinate system, while incredibly useful, is not built upon a perfectly fixed foundation. Precession is caused by the gravitational tug of the Sun and the Moon on Earth's equatorial bulge. Our planet is not a perfect sphere. It is slightly wider at the equator, and this extra mass, when pulled by external forces, causes the Earth's axis to slowly wobble, much like a spinning top beginning to slow down. This wobble is incredibly slow, tracing a complete circle in the sky every 25,800 years. But its effects are profound. It means that the celestial poles are not fixed points. The North Star, Polaris, which currently lies within a degree of the North Celestial Pole, has not always been our guide. In the time of the ancient Egyptians, the star Thuban in the constellation Draco was the pole star. And in about 12,000 years, the brilliant star Vega in the constellation Lyra will take its turn marking north. The entire celestial grid, the very equator, and the poles themselves shift imperceptibly over the millennia. This meant that the coordinates of every single star were slowly and inexorably changing over centuries. A star's right ascension and declination were not eternal truths, but merely a current address, valid for a particular epoch in time. For most practical purposes, the change was too slow to matter within a human lifetime, but for precise astronomical work, especially across generations, it had to be accounted for. This led to the practice of defining coordinates for a specific epoch, a fixed point in time that serves as a reference. When an astronomer today looks up the coordinates of a distant galaxy, they are given for that specific moment, and sophisticated software calculates the tiny adjustments needed for precession to point their telescope accurately to night. It is a beautiful and humbling reminder of our place in time, that even the most permanent-seeming structures in our sky are in a gentle, eternal dance, and that our maps must be updated not just for new discoveries, but for the very motion of the Earth itself. The constellations therefore serve a dual purpose. They are both the fixed landmarks for our navigation and the most visible proof that nothing is truly fixed at all, that we are living on a spinning, wobbling planet adrift in a dynamic and evolving universe. As our technology advanced, so too did the precision with which we could measure these celestial addresses. The invention of the telescope in the early 17th century did not make the constellations obsolete. Instead, it made them more important than ever. Suddenly, the sky was filled with countless faint stars invisible to the naked eye, along with nebulous clouds and distant galaxies that looked like mere smudges of light. How could an astronomer point their new, powerful instrument at one of these faint, anonymous objects? They would first find its location relative to the bright, familiar stars of a known constellation. The constellation provided the starting point, the well-known territory from which to venture into the unknown. An astronomer would consult a detailed star chart of, say, the constellation Andromeda. They would see that just northwest of the star Nu Andromedae lay a faint, extended patch of light. Using the known coordinates of Nu Andromedae, they could then carefully adjust their telescope's setting circles, graduated dials that functioned like a protractor for the sky, to point precisely at that spot. And there, swimming into view, would be the great Andromeda Galaxy, a whirlpool of 1 trillion suns, its light having traveled for 2.5 million years to reach the eyepiece. This process of star hopping, of using the bright stars of the constellations as stepping stones to fainter and more distant wonders, is a practice that continues to this day among amateur astronomers and was the bedrock of professional astronomy for centuries. The constellations became the chapters in the great book of the sky, and within each chapter, every object of interest needed a precise designation. This led to the creation of elaborate catalogs, each object often named for its constellation home. The famous Messier catalog, compiled by Charles Messier in the 18th century, is a list of fuzzy objects that could be mistaken for comets. Each entry is tied to its constellation. M42 is the Great Orion Nebula. M31 is the Andromeda Galaxy. M13 is the Great Globular Cluster in Hercules. Later, the new general catalog provided even more precise locations for thousands of nebulae and star clusters, their numbers forever associating them with their celestial homeland. To say, "I observed NGC 1976" is precise, but to say, "I observed the Orion Nebula" evokes its place in the great celestial tapestry, its position near the hunter's sword, its relationship to the bright stars Theta Orionis. The coordinates tell you where to look, but the constellation tells you what you are looking at in the context of the human experience of the sky. It connects the cold, precise mathematics of declination and right ascension to the ancient stories and the familiar patterns that first inspired us to look up in wonder. This marriage of the poetic and the precise is one of the most enduring and beautiful aspects of astronomy, a discipline that constantly navigates between hard data and profound awe. The meticulous practice of cataloging the heavens, of assigning every shimmering point and faint smudge of light its precise celestial coordinates within the borders of a constellation, reached its zenith with the advent of photography and massive, systematic sky surveys. The great observatories of the 19th and early 20th centuries turned their giant telescopes and photographic plates to the sky with a new ambition, not just to catalog the bright and the obvious, but to map everything. Projects like the Carte du Ciel, an international effort to photograph and measure every star down to the 14th magnitude, were monumental undertakings that relied entirely on the grid of constellations and the coordinate system they supported. Each plate captured a small section of a single constellation, its glass negative soon to be dotted with thousands of tiny black stars on a clear background, each one a potential new data point. Astronomers would then use measuring engines, precise instruments that could determine the exact position of each star on the plate, to refine its coordinates with astonishing accuracy. This was astronomy on an industrial scale, and the constellations provided the filing system. The universe, once a realm of wonder and myth, was becoming a dataset, but a dataset whose organizational structure was still written in the ancient language of Orion, Ursa Major, and Cygnus. It was within this vast and growing catalog of stellar positions that astronomers made one of their most profound discoveries, one that again changed our understanding of the cosmic map. By comparing the precise coordinates of stars measured years or even decades apart, they noticed something extraordinary. Many stars were not fixed. They were moving. This proper motion, as it is called, is the tiny, gradual shift of a star's position against the backdrop of much more distant stars. It is not the daily motion caused by the Earth's rotation, which affects everything equally, but the star's own individual journey through the galaxy. Barnard's star, a faint red dwarf in the constellation Ophiuchus, was found to have the largest proper motion, skirtling across the sky at a rate of about 10.3 arc-seconds per year, fast enough to move the width of a full moon in a human lifetime. This discovery added a new dynamic layer to our celestial coordinates. A star's position was no longer just a simple set of two numbers. It was a point in a fluid, evolving map. To know where a star truly is, one must know not only its coordinates for a given epoch, but also its velocity, its direction of travel. The constellations, then, are not permanent patterns, but rather temporary gatherings, like a flock of birds flying in loose formation. The stars that make up the familiar shape of the Big Dipper, for instance, are all moving at different speeds and in different directions. Tens of thousands of years from now, that famous ladle shape will have distorted beyond recognition, its stars scattering to new corners of the sky, to be grouped into new patterns by future generations with new myths to tell. This understanding of stellar motion leads us to the ultimate purpose of this precise celestial cartography: measuring distance. Knowing where something is on the two-dimensional dome of the sky is one thing, but understanding the true three-dimensional structure of the universe requires knowing how far away it is. The most fundamental method for measuring these vast distances is stellar parallax, a concept of elegant simplicity that is a direct consequence of the Earth's annual journey around the Sun. As our planet moves from one side of its orbit to the other, a distance of about 186 million miles, the perspective from which we view the stars changes minutely. A nearby star will appear to shift its position slightly against the background of much more distant stars. It is exactly the same effect as holding your finger up in front of your face and closing one eye and then the other. Your finger appears to jump back and forth against the background. The amount of this tiny shift, this parallax, is inversely proportional to the star's distance. The smaller the shift, the farther away the star. But to measure this shift, which is incredibly tiny, less than 1 arc-second even for the closest stars, astronomers need an incredibly stable and precise reference grid. They need a background of stars that are so immensely far away that they show no measurable parallax themselves. They appear truly fixed. These distant stars become the stationary backdrop against which the tiny wobble of the nearer star can be measured. And how do astronomers identify and catalog these background reference stars? By their precise coordinates within their constellations. The constellation provides the field of view, the neighborhood in which this delicate measurement takes place. By painstakingly measuring the minuscule change in a star's right ascension and declination over 6 months, astronomers can triangulate its distance, building a ladder of measurement that begins in our own solar system and reaches out into the galactic neighborhood. It is a slow, patient dance of measurement, all conducted within the silent, stable theater of the constellations. The successful measurement of stellar parallax was a monumental leap, a first step on the cosmic distance ladder that finally gave humanity a true sense of the staggering scale of the universe. It transformed the sky from a beautiful, two-dimensional tapestry into a profound, three-dimensional volume, with stars scattered at vastly different depths. The bright star Alpha Centauri, part of the constellation Centaurus, was found to be our nearest stellar neighbor, a mere 4.3 light-years away. Sirius, the brightest star in the night sky, located in Canis Major, blazes from a distance of 8.6 light-years. But this new depth perception revealed a new mystery, one that would require yet another ingenious use of the celestial coordinate system. Once astronomers knew the distance to a star, they could calculate its intrinsic brightness, or luminosity. And when they did this for many stars, they discovered a beautiful and powerful relationship between a star's color, which indicates its surface temperature, and its true brightness. This relationship is expressed in the Hertzsprung-Russell diagram, a graph that plots stars according to these two properties. Most stars fall along a main sequence, a clear diagonal band where hotter stars are brighter and cooler stars are dimmer. But some stars did not sit. They were far too bright for their color. A star might appear faint in our sky, suggesting it was a cool, modest star, but if its parallax measurement placed it very close to us, its faintness must be due to its small size and low energy output. Conversely, a star that appeared faint but was measured to be incredibly distant must, in reality, be a luminous giant, pouring forth staggering amounts of energy to be visible to us at all. This is where the constellations became crucial once more. By knowing a star's coordinates, astronomers could measure its apparent brightness. By using parallax or other methods, they could determine its distance. And from these two pieces of information, they could calculate its true power, its luminosity. This allowed them to classify stars not by how they appear to our limited eyesight, but by what they truly are: red dwarfs, yellow main sequence stars like our Sun, blue giants, or red supergiants like Betelgeuse in Orion, which, despite its cool surface temperature, is so colossal that it outshines the Sun thousands of times over. The constellations provided the fixed stage upon which this cosmic inventory could be taken, star by star, coordinate by coordinate, revealing the immense variety of stellar engines that power the galaxy. This understanding of true stellar luminosity became the next crucial rung on the distance ladder, allowing astronomers to reach beyond the limited range of the parallax method. If you know what a star should look like, its true brightness based on its classification, and you measure how dim it appears to be in the sky, you can calculate how far away it must be to appear that faint. This method, using stars like Cepheid variables, whose pulsation periods are directly tied to their luminosity, allowed astronomers to measure distances to other galaxies. It was by observing Cepheid variables in the Andromeda galaxy, a faint smudge within the borders of the constellation Andromeda, that Edwin Hubble conclusively proved in the 1920s that this nebula was not a cloud within our own Milky Way, but an entire island universe of its own, millions of light years away. This single discovery, made by pinpointing specific stars within a specific constellation, exploded the known size of the universe. The constellations, those ancient patterns, had become the gateway to a cosmos of unimaginable vastness. Every time an astronomer identifies a Cepheid variable in a distant galaxy, they are using a technique that relies on the foundational grid of celestial coordinates to make that measurement, to take that photograph, to compare its brightness to the known standard. The constellation is the address that leads them to the right galaxy, and the coordinates within that constellation allow them to find the specific star that holds the key to its distance. In the modern era, this entire process has been automated and scaled to a degree that would astonish the astronomers of the past. Space-based telescopes like Gaia are currently engaged in the most detailed celestial survey ever conceived. From its vantage point at a stable gravitational point in space, Gaia is not just measuring the parallax of stars. It is measuring the parallax, proper motion, and velocity of over 1 billion stars in our galaxy with micro-arcsecond precision. Its mission is to create a three-dimensional dynamic map of the Milky Way. But how does it do this? It still relies on the fundamental concept of a reference frame. Gaia constantly scans the sky, measuring the angles between the incredibly distant fixed quasars, active galactic nuclei, billions of light years away, that serve as the ultimate anchor points, and the billion stars in our own galaxy. It is building a map by constantly triangulating everything against this stable grid. And how do astronomers communicate about the targets for such a mission? They use the constellations. They speak of studying stellar populations in the direction of Sagittarius, toward the galactic center, or of mapping the spiral arm structure in the distant reaches of Perseus or Carina. The constellation names provide the intuitive, human-readable context for the unimaginably vast streams of data flowing from the spacecraft. The billions of precise measurements are stored in databases where each entry is tagged with its right ascension and declination, a digital testament to a system of navigation born from connecting the dots between bright stars under a dark, ancient sky. The poetry of the myths and the precision of the mathematics have become inextricably linked in our quest to understand the cosmos. As our cosmic maps grew to encompass not just our galactic neighborhood, but the entirety of the Milky Way and beyond, the role of the constellations evolved from providing a simple address to defining the very axes of cosmic geography. Our solar system does not sit at the center of the galaxy. It is located in the quiet suburbs of a spiral arm about halfway out from the core. From this vantage point, the Milky Way itself appears as a hazy, luminous band arcing across the sky. This band is not random. It is the plane of our disc-shaped galaxy, and it passes through specific constellations, Sagittarius and Scorpius, where the center glows brightly, through Cygnus and Cassiopeia, and onward to Orion and Vela. To an astronomer studying the structure of the Milky Way, these constellations are not just patterns, they are directions. Looking toward the constellation Sagittarius means looking toward the galactic center, a region teeming with stars, dust, and a supermassive black hole. Looking in the opposite direction, toward the constellation Auriga, means looking out toward the galactic anti-center, away from the crowded core and out toward the sparser outer reaches of the galactic disk. Thus, a new coordinate system was born, one overlaid upon the ancient celestial grid, the galactic coordinate system. Here, the fundamental plane is not the Earth's equator projected into space, but the plane of the Milky Way itself. Galactic latitude measures a star's distance north or south of this galactic plane, while galactic longitude measures its angular distance around the plane from the agreed-upon galactic center in Sagittarius. This system is incredibly powerful for studying the architecture of our own galaxy. allowing astronomers to map the spiral arms, the distribution of gas clouds, and the populations of stars in a framework that is native to the galaxy itself. Yet, even the system is tied to the old. The 0 point for galactic longitude is defined by its precise celestial coordinates within the constellation Sagittarius. The new is forever referenced to the old, a continuous thread of knowledge connecting the naked eye observer to the astrophysicist studying galactic dynamics. This expansive view naturally leads us to look even further beyond the confines of our own galaxy to the vast ocean of space that holds countless other islands of stars. And here, in the realm of the extragalactic, the constellations take on their most profound role yet. They become the windows through which we peer into the deep universe. When an astronomer points the Hubble Space Telescope at a seemingly empty patch of sky within the constellation Ursa Major, they are not looking for a star within our galaxy. They are using that patch of sky, defined by its precise right ascension and declination, as a porthole. The constellation provides a stable, well-understood pointing direction free from the obscuring light of bright Milky Way stars. The result of such an observation is the famous Hubble Deep Field image, a photograph that revealed thousands of galaxies in an area of sky no larger than a grain of sand held at arm's length. Each of those tiny, faint smudges is an entire galaxy, similar to or larger than our own Milky Way, each containing hundreds of billions of stars. This one image, targeted by its celestial coordinates within a familiar constellation, forever changed our perception of the universe's scale and content. It revealed a cosmos teeming with galaxies as far as our telescopes can see. Subsequent deep fields have been taken in other constellations, Fornax, Tucana, and others, each providing a different keyhole view into the universe's depths. The constellation is the guidepost that tells us where to look for these profound vistas, ensuring that different telescopes and different astronomers can return to the exact same spot on the celestial sphere, generation after generation, to build upon the discoveries of the past. The ultimate expression of this cosmic cartography lies in the study of the universe itself as a whole, the field of cosmology. To understand the origin, evolution, and fate of the entire cosmos, astronomers must map the universe on the largest possible scales. They must trace the cosmic web, the vast filamentary structure of dark matter along which galaxies and galaxy clusters are strung like pearls on a necklace, separated by enormous cosmic voids. This mapping requires pinpointing the three-dimensional location of millions of galaxies. The process begins, always, with the two-dimensional coordinates on the sky, right ascension and declination, within a constellation. The Sloan Digital Sky Survey, for instance, did not scan the sky randomly. It meticulously mapped large swaths of specific constellations like Virgo, Coma Berenices, and Hercules, measuring the positions of hundreds of millions of objects. But to get the third dimension, distance, astronomers used the redshift of a galaxy's light. As the universe expands, it stretches the wavelength of light from distant galaxies, shifting it toward the red end of the spectrum. The greater the redshift, the farther away the galaxy, and the further back in time we are seeing it. By combining the angular position from the celestial coordinate system with the redshift-derived distance, astronomers can place each galaxy in its true location in the cosmos. This is how we have mapped the large-scale structure of the universe, revealing the Great Wall of Galaxies, the vast Bootes Void, and the elegant, web-like filaments that span hundreds of millions of light-years. Every dot on these three-dimensional maps of the cosmos began as a set of numbers, a right ascension and a declination, a unique address within the borders of an ancient constellation. It is a humbling thought that the stories of heroes and beasts, imagined by people millennia ago, have become the foundational grid for charting the entirety of observable existence, from our local stars to the very edge of space and time. The constellations are the quiet, constant guides in our ever-expanding exploration of the infinite. In this age of digital astronomy and robotic exploration, one might assume that the ancient art of navigating by the constellations has become obsolete, replaced by microchips and precise orbital mechanics. But the truth is far more beautiful and interconnected. Modern spaceflight has not discarded the old ways. It has integrated them into a seamless tapestry of navigation, using the stars as a fundamental and fail-safe reference system. Every spacecraft, from a Mars rover to a probe on its way to the outer solar system, carries within its computer memory a sophisticated star catalog. This catalog is not a list of constellation names and myths, but a database of precise celestial coordinates and brightness values for thousands of the brightest, most reliably fixed stars. These are the guideposts of the cosmos, and the spacecraft uses them to know its own orientation in the void, a practice known as celestial navigation. A small telescope or star tracker on the spacecraft scans the blackness around it, identifying patterns of stars. It doesn't see the shape of Orion the Hunter, it sees a specific configuration of bright points of light. It measures their relative positions, and by comparing this pattern to the map in its memory, it can compute its precise attitude, its roll, pitch, and yaw in space. It is, in essence, performing the same function as a human navigator on a ship thousands of years ago, but at a speed and precision that is almost unimaginable. The constellations, broken down into their mathematical essence, remain the pole stars for our mechanical ambassadors, a silent, reliable presence that orients them in the profound emptiness between worlds. This stellar reference frame is absolutely critical for the most delicate of operations. When the James Webb Space Telescope needs to hold perfectly still for days on end to collect the faint photons from the earliest galaxies, it must counteract even the tiniest drift. It does so by constantly checking its position against the fixed background of stars, making minute adjustments with its reaction wheels to stay locked on target. Its targets are defined by their celestial coordinates, coordinates that are meaningful only within the context of the stable celestial sphere. The same is true for the Hubble Space Telescope, for interplanetary probes, and for telescopes on the Moon that may one day peer even deeper into the cosmos. They all speak the universal language of right ascension and declination, a language whose dictionary is written in the constellations. Even missions that venture far from Earth retain this connection. The Voyager probes, now in interstellar space, used sightings of bright stars like Canopus to help maintain their orientation on their long journey away from the Sun. As they travel, the patterns of the stars shift slightly from their perspective, a subtle testament to their incredible journey. But the fundamental catalog of celestial coordinates remains their anchor, their one constant in a changing sky. Yet, for all their stability, the constellations and the coordinate system they support must also account for the most extreme and bizarre phenomena in the universe. When a massive star collapses at the end of its life, or when two ultra-dense neutron stars spiral into each other, they can trigger a cataclysm so violent that it ripples the very fabric of space-time itself, sending gravitational waves propagating across the cosmos at the speed of light. When observatories like LIGO and Virgo detect these faint whispers from a billion light-years away, they are faced with a monumental task: pinpointing where in the sky the event occurred. The detectors themselves can tell us the nature of the event and its approximate distance, but they are notoriously poor at pinpointing a location on the two-dimensional sky. They can only narrow it down to a vast, banana-shaped swath of space that might cover hundreds or even thousands of square degrees, an area that can contain dozens of constellations. This is where the traditional celestial map becomes essential. Astronomers immediately mobilize telescopes across the globe and in space, directing them to scan that large, fuzzy patch of sky. They're looking for a new pinprick of light, a kilonova, the telltale glow of radioactive debris from a neutron star merger. To coordinate this worldwide effort, they use the common language of astronomy, right ascension and declination. They will announce to the world that the event is likely located in a specific part of the constellation Hydra or Lacerta. Instantly, every astronomer knows where to look. The familiar patterns provide the search grid. Without the shared coordinate system, born from the constellations, the frantic and exciting hunt for the electromagnetic counterpart to a gravitational wave event would be like searching for a needle in a haystack the size of the planet, with no idea where to even begin. The constellations provide the context that turns a fuzzy probability map into a specific point of interest, allowing humanity to witness the birth of black holes and the forging of heavy elements like gold and platinum in the cosmic furnaces of colliding stars. This brings us to the most profound and humbling realization of all. The map we have built, for all its precision, is a local map. The celestial coordinates, the constellations, the very galactic plane, they are all defined by our particular perspective from a small planet orbiting an average star in the outskirts of a spiral galaxy. This is our cosmic address, but it is not a universal one. An intelligent astronomer on a planet orbiting a star in the Andromeda galaxy would draw a completely different set of constellations in their night sky. Their pole star would be different, their celestial equator would be tilted at another angle, their view of the Milky Way would be a spectacular external perspective, a grand spiral pattern that might form the centerpiece of their own mythology in astronomy. Their coordinate system would be just as valid as ours, but it would be entirely their own, built from their unique vantage point in the universe. This is not a limitation of our science, but rather its deepest beauty. It reminds us that our understanding of the cosmos, though vast and powerful, is inherently rooted in our own experience. We have learned to navigate the infinite from our own finite corner of it. The constellations are our guide, our story, our starting point. They are the familiar porch light that allows us to venture out into the darkness, always providing a way to find our way home, while simultaneously guiding us to understand that home is just one small part of a much grander, more mysterious, and wonderfully interconnected whole. Our maps are imperfect and perspective-bound, but they are the best tools we have, and they have unlocked the universe. As we settle deeper into our contemplation of the night sky, it's natural to wonder how this grand celestial coordinate system, for all its precision, manages to feel so personal, so accessible. The answer lies in the beautiful interplay between the absolute rigidity of mathematics and the fluid, intuitive art of visual recognition. While a computer might only understand a star as a set of numbers, our human minds are not designed to navigate by strings of digits. We navigate by stories, by shapes, by patterns. This is the enduring, irreplaceable gift of the constellations. They are the mnemonic poems of the sky, the visual hooks upon which we hang the vast and weightless cloak of scientific data. When they are told to look for the 3 bright stars of Orion's belt and then just below to the fuzzy patch in his sword, the sky suddenly makes sense. The constellation provides the context, the familiar neighborhood. The coordinates then provide the exact street address within that neighborhood for those who possess the instruments to need such precision. This dual-layer system is what makes astronomy both a rigorous science and a deeply humanistic pursuit. It allows the backyard stargazer with a simple star chart and the PhD astrophysicist controlling a billion-dollar telescope to speak the same language, to share the same wonder, even if their tools are vastly different. The constellations are the great democratizers of the cosmos, ensuring that the map of the universe remains open and readable to anyone who simply takes the time to look up and learn the landmarks. This human-scale connection to the cosmos extends beyond mere static observation and into the very rhythm of time itself. Our most fundamental units of time, the day, the month, the year, are all dictated by celestial motions, and the constellations are the clock face upon which this time is displayed. The apparent journey of the sun through the stars over the course of a year traces a path called the ecliptic, which passes through 12 familiar constellations, the signs of the zodiac. While modern astrology has imbued these with symbolic meaning, their original astronomical significance is profound and practical. The sun's arrival in a particular zodiac constellation marked the turning of the seasons for ancient cultures. When the sun appeared in the constellation Virgo, it was a signal of the impending harvest. Its movement into Pisces heralded the rains of spring. The celestial calendar was encoded in stone circles and temple alignments, a global phenomenon that connected humanity to the cosmos through the slow, predictable dance of the constellations. Even today, though our calendars are digital and atomic, the astronomical reality persists. The winter solstice, the shortest day of the year in the northern hemisphere, occurs when the sun is at its most southerly point in the sky, positioned in the constellation Sagittarius, near the rich star fields of the galactic center. The summer solstice finds the sun in Gemini, high in the sky. This annual cycle, written in light against the backdrop of the constellations, is a deep rhythmic pulse that has guided life on Earth for billions of years, and our awareness of it, through the naming of these constellations, is a testament to our desire to find our place within this cosmic cycle. The predictability of the celestial clockwork also allows for one of the most enchanting and useful applications of the constellations: their role in locating the wanderers, the planets of our own solar system. Unlike the fixed stars, which maintain their relative positions for centuries, planets like Jupiter, Venus, and Mars move against the stellar backdrop from night to night and week to week. But they do not wander randomly. Their paths are confined to a narrow band of the sky, the ecliptic, the same highway traveled by the sun and moon, which is defined by the plane of our solar system. And this highway runs directly through the constellations of the zodiac. To find a planet on any given night, one need only know which zodiac constellation is prominent in the evening or morning sky. A bright, steady light that doesn't twinkle like the surrounding stars, sitting in the constellation Leo, is almost certainly the planet Saturn. A brilliant evening star blazing in the west within the boundaries of Taurus is invariably Venus. The constellations provide the stationary backdrop against which this planetary motion becomes visible and meaningful. They allow us to track the graceful loops and retrograde motions of Mars, to witness the slow, stately procession of Jupiter from one zodiacal house to the next over the course of a year. This dance of the planets was a profound mystery to ancient astronomers, one that eventually led to the understanding that Earth was not the center of all things. Today, it provides a constant, visible connection to our celestial neighborhood, a reminder that we are part of a dynamic system of worlds, all orbiting our common star, their journeys forever framed by the ancient, unchanging patterns of the zodiacal constellations. It is a nightly ballet performed on the grandest stage, with the constellations as the ornate, glittering proscenium arch. As we grow more familiar with the constellations and the coordinate system they support, we begin to perceive a deeper layer of information encoded within the starlight itself. A layer that speaks not just of position, but of motion, history, and physical nature. This information is unlocked through the subtle language of color and brightness, a language that the celestial coordinates allow us to translate for each individual star. When we look at the constellation Orion, for instance, we immediately notice the striking difference between Betelgeuse, a brilliant orange-red gem on his shoulder, and Rigel, a dazzling blue-white point of light at his foot. This difference in color is not a trick of the eye or an effect of the atmosphere. It is a fundamental physical property. A star's color is a direct indicator of its surface temperature. Blue stars, like Rigel, are scorching hot, with surface temperatures reaching 40,000 degrees Kelvin or more. Red stars, like Betelgeuse, are comparatively cooler, though still incredibly hot at around 3,500 degrees Kelvin. Yellow stars, like our Sun, fall somewhere in between. But to understand what these colors truly mean, we must know where to look, and the constellations provide the essential context. By identifying a star by its place within a constellation, astronomers can isolate it for further study. They can measure its apparent magnitude, how bright it appears to us here on Earth. This measurement, however, is only the beginning, for a star's apparent brightness depends on two things: its true intrinsic power and its distance from us. A faint star could be a powerful giant, tragically dimmed by immense distance, or it could be a modest dwarf star, relatively close to us. This is where the precise celestial coordinates become absolutely vital. To unravel this mystery, astronomers use the technique of spectroscopy. By attaching a spectrograph to a telescope and pointing it precisely to the coordinates of a specific star within a constellation, say the star Alnitam, the central star in Orion's belt, they can break its light down into a rainbow spectrum. Within the spectrum are dark lines, like a unique barcode, that reveal the star's chemical composition, surface gravity, and most importantly, its spectral class, which confirms its temperature and intrinsic color. Once the star's true nature is known from its spectrum, its apparent brightness, measured through its precise photometric magnitude, can be used to calculate its distance. A star identified as a blue supergiant by its spectrum that appears faint must be extraordinarily far away. A star that is revealed to be a red dwarf but appears relatively bright must be one of our close neighbors. This process of using coordinates to find a star, spectroscopy to understand its physics, and photometry to measure its distance is how we build a three-dimensional picture of our galactic neighborhood. The constellation of Orion therefore transforms from a two-dimensional picture into a rich stellar population. We learn that Rigel is a distant supergiant over 800 light-years away, burning with an intensity that dwarfs our Sun. Betelgeuse is a variable red supergiant, closer at about 500 light-years, and so vast that if placed at the center of our solar system, its outer atmosphere would engulf the orbit of Jupiter. The three stars of the Belt, Alnitak, Alnilam, and Mintaka, are not a chance alignment from our perspective, but are genuinely associated, part of a loose cluster born from the same cosmic cloud. The coordinates allow us to move from the myth of the hunter to the astrophysics of stellar evolution, all within the same familiar pattern of stars. This ability to move from the general to the specific, from the constellation to the individual coordinate, also allows astronomers to track the transient, the variable, and the entirely new. The sky may seem constant, but it is a stage for constant, often violent change. Stars pulse in brightness over days or years. Novae, thermonuclear explosions on the surface of white dwarf stars, can suddenly flare into visibility where nothing was seen before. Supernovae, the catastrophic deaths of massive stars, can briefly outshine entire galaxies. When such an event occurs, the first step is always to pinpoint its location with extreme precision. Astronomers will announce the discovery of a new nova, but to understand the context of this event, to know what star system has undergone this eruption, they will immediately note that these coordinates place it within the bounds of the constellation Hercules, just northeast of the star Corniferos. This contextual information is crucial. It allows other observers to find it easily. It tells them what field of view to use on their telescopes. Perhaps most importantly, it allows them to consult existing star catalogs and archival images of that exact spot in Hercules. They can see what was there before the eruption. Was it a faint, unnoticed binary system? Was it a known variable star? The constellation provides the filing cabinet, and the coordinates provide the specific folder, allowing for instant historical comparison. This is how new worlds are discovered too. The tiny, regular dimming of a star's light caused by an orbiting planet passing in front of it is detected by meticulously monitoring the brightness of that star over months and years. This monitoring is only possible because we can return again and again to the exact same coordinates within its home constellation, measuring its light with exquisite precision against the stable backdrop of its stellar neighbors. Every exoplanet discovery, every nova alert, every variable star chart begins with a set of numbers that place it on the eternal map drawn by the constellations, a map that makes the dynamic universe manageable, measurable, and profoundly knowable. Beneath the familiar tapestry of constellations and the precise grid of coordinates lies a deeper, invisible architecture that holds the universe together. This is the realm of dark matter, the mysterious, unseen substance that makes up the vast majority of the universe's mass. We cannot see it, touch it, or directly detect it with any instrument we have yet devised, for it does not emit, absorb, or reflect light. Its presence is known only through its profound gravitational influence on the things we can see, the stars and the galaxies. And how do we measure this influence? We do so by carefully observing the motions of visible objects, motions that are meticulously tracked using the very celestial coordinate system the constellations provide. The story of dark matter's discovery begins close to home, within our own galaxy. By measuring the rotation curves of galaxies, plotting the orbital speed of stars and gas clouds against their distance from the galactic center, astronomers made a startling discovery. According to the laws of gravity, stars on the outer edges of a spiral galaxy, far from the central mass, should orbit more slowly, just like Pluto orbits the Sun more slowly than Earth does. But the observations revealed something entirely different. Stars at the very outskirts of galaxies orbit just as fast as those near the center. This meant that there had to be far more mass in the galaxy than could be accounted for by the visible stars, gas, and dust. This mass, this gravitational anchor, had to be in the form of an enormous, invisible halo of dark matter enveloping the entire luminous galaxy. Every measurement of a star's velocity, every precise determination of its position and motion within its galactic structure relies on the foundational ability to pinpoint that star's location in the sky, to track its subtle proper motion over years, all within the contextual frame of its constellation. This gravitational evidence extends far beyond individual galaxies to the largest structures in the universe, galaxy clusters, which are vast cities of galaxies bound together by gravity. When astronomers pointed their telescopes at a famous cluster like the Coma cluster, located in the constellation Coma, Berenices, they witnessed a similar paradox. The individual galaxies within the cluster were moving so rapidly that the visible mass of all the stars and gas in all the galaxies was nowhere near enough gravity to hold the cluster together. Without a tremendous amount of unseen mass, the cluster should have flown apart billions of years ago. Yet there it sits, stable and coherent. Furthermore, we can map the distribution of this dark matter through a phenomenon called gravitational lensing. Albert Einstein's theory of general relativity tells us that mass curves the fabric of space-time. When light from a distant galaxy travels through the universe, its path is bent if it passes near a massive object, like a galaxy cluster. This bending acts like a lens, distorting the image of the background galaxy into faint, stretched arcs. By studying these arcs, by measuring their precise shapes and positions using the celestial coordinate grid, astronomers can create a map of the mass causing the distortion. Incredibly, these maps reveal that the visible galaxies in the cluster are merely embedded like glittering ornaments within a much larger, massive, and completely dark scaffold of matter. The constellation Coma Berenices, then, is not just the home of a beautiful cluster of galaxies, it is the window to a hidden world of dark matter, a world whose presence is deduced through the meticulous measurement of light and its journey across the cosmos, a journey we can only trace because we have a stable map to define where that light began and how it was bent along the way. The influence of this dark architecture extends to the very expansion of the universe itself, a discovery that introduced another profound mystery: dark energy. In the late 1990s, two independent teams of astronomers were using distant supernovae, stellar explosions of consistent brightness, to measure the expansion rate of the universe over cosmic time. To do this, they had to find these supernovae in the faint, faraway galaxies of the deep field. Their search was conducted by taking images of the same patches of sky, defined by their coordinates in constellations like Cetus and Ursa Major, weeks apart and looking for new points of light. When they measured the distances and redshifts of these supernovae, they made a shocking discovery. The expansion of the universe was not slowing down as everyone had expected due to the gravitational pull of all matter. It was accelerating. Something was counteracting gravity, pushing galaxies apart at an ever-increasing rate. This something was dubbed dark energy. This monumental discovery, which earned the Nobel Prize, was made by using the celestial coordinate system as a ruler. They measured how the brightness of their standard candles, the supernovae, dimmed with distance, and how their light was stretched to redder wavelengths by the expansion of space. Every data point was a set of coordinates, a precise location in a specific constellation, a faint speck of light that held the key to the universe's fate. The constellations, those ancient patterns, became the reference points for measuring the force that will ultimately determine the long-term destiny of all cosmic structure. They provide the fixed background against which the most fundamental motions of the cosmos, the slowing pull of dark matter and the accelerating push of dark energy, are measured, reminding us that the sky is not a static painting, but a dynamic, evolving arena where visible light is merely the smallest hint of the profound and hidden forces at work. As we learn to read the deeper messages held within the starlight, the motions dictated by dark matter, the expansion driven by dark energy, we inevitably turn our gaze inward to understand the structure of our own cosmic home, the Milky Way galaxy. And here, the constellations play their most personal and perhaps most challenging role. Unlike an observer outside our galaxy who could see its majestic spiral structure whole, we are embedded within its disk, like a single piece of pollen inside a vast spinning flower. Our view is necessarily edge-on, and our perspective is profoundly limited by immense clouds of interstellar gas and dust that obscure the visible light from distant regions. This is where the celestial coordinate system transforms from a simple map into a sophisticated tool for cosmic cartography. To piece together the architecture of the Milky Way, astronomers must act as surveyors of a vast and foggy landscape, using the constellations as their fixed reference points to triangulate their position and map what lies around them. The first great step in this process was to measure the scale of our galaxy, a task that fell to the early 20th century astronomer Harlow Shapley. He did this by mapping the distribution of globular clusters, ancient, dense spheres of hundreds of thousands of stars that form a vast halo around the galactic disk. By using variable stars within these clusters to determine their distances, and by meticulously plotting their positions on the celestial sphere, Shapley made a revolutionary discovery. These clusters were not centered on our solar system. They were overwhelmingly concentrated in the direction of the constellation Sagittarius. He correctly deduced that this meant the true center of our galaxy lay in that direction, some tens of thousands of light years away. This was a monumental shift in perspective, moving humanity from a presumed central place in the galaxy to a remote suburb. It was a feat of cosmic navigation achieved by using the fixed grid of the constellations to plot the three-dimensional positions of these far-flung island beacons, forever associating the galactic core with the teapot-shaped asterism in Sagittarius. Mapping the spiral arms themselves is an even more complex task, one that relies on the same principles of celestial navigation used by sailors for millennia, but on a galactic scale. The primary method involves using radio astronomy. The clouds of hydrogen gas that trace the spiral arms emit a faint radio signal at a specific wavelength, 21 centimeters. This radio light has a tremendous advantage. It passes through the obscuring dust that blocks visible light. Giant radio telescopes scan the sky, constellation by constellation, measuring the precise wavelength of this 21-centimeter emission. But because the galaxy is rotating, the gas in different arms is moving at different speeds relative to us. This motion causes a Doppler shift in the radio waves, slightly stretching or compressing the wavelength. By measuring this shift with extreme precision for every point in the sky, astronomers can calculate the velocity of the gas. Then, using models of the galaxy's rotation, they can translate that velocity into a distance. It is a slow, painstaking process of building a three-dimensional map from a two-dimensional set of observations. Every data point is tagged with its celestial coordinates, a specific right ascension and declination in, say, the constellation Cygnus, combined with a velocity-derived distance. When this is done for the entire sky, the spiral arms begin to emerge from the data. We find that we live in the Orion Cygnus arm, a minor spur between the larger Perseus and Sagittarius arms. The constellation Orion, then, is not just a hunter in the sky. It is the name of our local galactic neighborhood. The familiar stars we see are our close neighbors within this arm, while the misty band of the Milky Way is the combined light of the billions of stars in the other arms. Their structure revealed not to our eyes, but to our radio telescopes and our understanding of the coordinate grid that lets us place each piece of data in its proper place. This mapping extends to the very motions of our own sun. Our solar system is not stationary. It orbits the galactic center at a speed of about 220 kilometers per second, taking roughly 230 million years to complete one galactic year. We can measure this motion by carefully observing the apparent movement of other stars. Over time, as we speed toward a point in the constellation Hercules, our solar apex, the stars in that general direction appear to drift slightly apart from each other, while the stars behind us in the opposite direction, toward the constellation Columba, appear to crowd closer together. The subtle effect, called secular parallax, is only detectable through long-term, precise astrometric measurements of stellar positions, all recorded within the immutable celestial coordinate system. The constellations, therefore, are not only the backdrop for our journey, they provide the directional signposts for it. They tell us where we are going, Hercules, and where we have come from. They allow us to situate ourselves within the grand, slow-churning vortex of the Milky Way, transforming our nightly experience of the sky from a static display into a dynamic snapshot of a journey we are all taking together around the galactic center. A journey whose direction and scale is written in the steady, patient drift of the stars themselves, a drift we can only measure because we have a fixed grid against which to measure it. Our celestial address is not just a location, it is a trajectory, and the constellations are the signs that let us read our course through the cosmos. Having mapped the contours of our own galaxy, our curiosity naturally extends outward to the countless other islands of stars that drift in the cosmic ocean. These galaxies, spirals, ellipticals, and irregular clouds of light, are the fundamental building blocks of the large-scale universe. To study them, to understand their distribution, motions, and histories, we must first be able to find them, to distinguish them from foreground stars in our own Milky Way, and to measure their properties with precision. Once again, the celestial coordinate system, anchored by the constellations, provides the essential framework for this grand census of the cosmos. The first step in studying any external galaxy is to record its position. When the Andromeda Galaxy was first catalogued, it was given its designation based on its location. It is the 31st object in Charles Messier's list of fuzzy non-comets, but its identity is forever tied to the constellation in which it resides. To point a telescope at M31 is to point it toward the constellation Andromeda. This was not merely tradition, it is practical necessity. The constellation provides the initial search field, the recognizable chunk of sky that contains the target. For every galaxy, from the majestic Whirlpool Galaxy in Canes Venaticus to the delicate Pinwheel Galaxy in Ursa Major, its celestial coordinates are its universal identifier, the key that allows any astronomer anywhere in the world to locate it and study it. This common reference system is what makes collaborative global astronomy possible, ensuring that an observation made in Chile can be seamlessly followed up by a telescope in Hawaii, because both are pointing toward the same right ascension and declination within the same constellation. The true power of these coordinates is unleashed when we combine them with the measurement of redshift. As we noted earlier, the light from distant galaxies is stretched to longer, redder wavelengths by the expansion of the universe. The degree of this redshift, denoted by the letter Z, is a direct measure of how much the universe has expanded since the light left that galaxy, and thus a measure of its distance and how long ago we are seeing it. A galaxy's celestial coordinates tell us where it is on the two-dimensional sky. Its redshift tells us how far away it is in the third dimension and how far back in time we are looking. When we combine these two pieces of information for millions of galaxies, plotting their right ascension, declination, and redshift in a vast three-dimensional database, the true architecture of the universe begins to emerge. This is how we have mapped the cosmic web, the largest structure in the universe. This web is a network of gigantic filaments of dark matter along which galaxies are strung like pearls, separated by enormous, nearly empty voids. These maps reveal a universe that is not random, but possesses a complex bubble-like structure on scales of hundreds of millions of light years. The Sloan Digital Sky Survey, which has meticulously measured positions and redshifts of over 3 million galaxies, uses the constellations as its organizing principle. Its data releases will describe the survey area as covering specific regions of the constellation Virgo, Coma Berenices, and Hercules. Every single galaxy in its catalog has a precise set of coordinates that places it not only in a numerical database, but within the ancient stellar patterns that grace our night sky. The constellations become the directory for the cosmos, the chapter headings in the story of universal structure. This three-dimensional mapping allows us to witness the dynamics of the universe on the grandest scale. We can see that galaxies are not simply moving apart with the general expansion, they're also flowing along the filaments of the cosmic web under the relentless pull of gravity. These motions, known as peculiar velocities, are superimposed on the Hubble flow of expansion. By carefully measuring them, astronomers can trace the gravitational tides that wash through the universe, mapping the distribution of both dark and visible matter on scales that defy comprehension. Furthermore, by looking to ever greater distances, by measuring the redshifts of galaxies so distant that their light has been traveling for over 10 billion years, we can essentially look back in time and see how the cosmic web has evolved. And it is the anchoring of these coordinates to the constellations that makes all of this investigation and this mapping possible.
We can observe the first galaxies forming and clustering. We can watch the voids grow emptier and the filaments grow more defined. This entire edifice of cosmological knowledge, our understanding of the universe's evolution from a nearly smooth primordial soup to the complex web of today, is built upon billions of individual measurements. And every one of those measurements, every spectrum taken, every redshift calculated, begins with the telescope being pointed to a specific set of celestial coordinates within a specific constellation. The familiar patterns of the night sky are thus the gateway to the deepest past, the fixed reference points that allow us to construct a movie of cosmic evolution spanning billions of years. They are the steady hand that holds the measuring rod against the expanding fabric of space-time itself, allowing us to trace the growth of the largest structures in existence, from their faint beginnings to their present-day majesty. As we push our observations to the very edge of the observable universe, to the most distant galaxies and quasars whose light is stretched into the infrared by immense redshift, we approach a fundamental limit, a horizon in both space and time. This horizon is not a physical barrier, but a temporal one. The era before galaxies existed, before stars had even formed, when the universe was a hot, dense, opaque fog of plasma. The light from this era cannot reach us in the form of stars and galaxies. Instead, it reaches us as a constant, ubiquitous glow that fills the entire sky, the cosmic microwave background radiation. This is the oldest light in the universe, the remnant heat from the Big Bang, released when the universe was a mere 380,000 years old and had cooled enough for atoms to form and photons to travel freely. This light is the ultimate background against which all later structures formed, and it too is mapped onto the celestial sphere using the same coordinate system defined by the constellations. Satellites like Planck have spent years meticulously measuring the temperature of this radiation across the entire sky, creating a map of the faintest variations, anisotropies, imprinted upon it. These tiny fluctuations, mere millionths of a degree, are the seeds of all future structure, the slightly denser regions that would, over billions of years, collapse under gravity to form the galaxies, clusters, and filaments of the cosmic web we see today. The map of the cosmic microwave background is the universe's deepest and most fundamental coordinate grid. It represents the initial conditions from which everything evolved. When cosmologists study this map, they do so by analyzing the temperature variations as a function of their position on the sky, their right ascension and declination. They speak of a particularly cold spot in the constellation Eridanus, or a specific hot region in the direction of Orion. These features are not just points on a map. They are windows into the physics of the universe's first moments, encoding information about the density, composition, and geometry of the entire cosmos. The precise statistical properties of these fluctuations, measured across the entire celestial sphere, have allowed us to determine the age of the universe, its composition of ordinary matter, and dark energy, and the parameters of its expansion with astonishing precision. It is the Rosetta Stone of cosmology, and we can only read it because we have a consistent, all-sky coordinate system in which to plot its intricate details. The constellations, in this context, provide the familiar language with which we discuss these most primordial of features, connecting the hottest and coldest spots on the infant universe's surface to the familiar patterns we see in the night sky today. They are the reference points for the universe's birth certificate. But this ancient light does more than just provide a map of the past. It also serves as a backdrop against which we can measure the motion of our entire local group of galaxies through the cosmos. Just as a car driving through rain experiences the rain seeming to come from slightly ahead, our motion through the universe creates a noticeable dipole anisotropy in the cosmic microwave background. The light appears very slightly hotter and blue shifted in the direction of our motion toward the constellation Leo, and very slightly cooler and red shifted in the opposite direction toward Aquarius. This is not a feature of the early universe. It is a Doppler shift imprinted on the ancient light by our own journey. By measuring the precise amplitude and direction of this dipole, astronomers can calculate our velocity relative to this fundamental rest frame of the cosmos. We are moving at about 600 kilometers per second toward the border between the constellations Leo and Crater. This measurement is a profound reminder of our place in a dynamic universe. Even the oldest light we can see is not static. It is affected by our motion, and that motion is measured and described using the same celestial coordinates that have guided navigators and astronomers for millennia. The constellations provide the direction for this grand universal current, reminding us that we are not passive observers, but active participants in the cosmic flow, riding our galaxy through the vast ocean of space, with the faded glow of creation itself as our witness and our guide. In this quiet contemplation of the cosmos and our methods of navigating it, we arrive at a deeply philosophical realization. The celestial coordinate system, for all its mathematical precision, is a profoundly human construct. It is a magnificent and necessary fiction, a model that allows our earthbound minds to comprehend the infinite. The concept of the celestial sphere, a giant imaginary dome encasing the Earth, onto which all stars are projected at an equal distance, is not physically real. Stars are not fixed on a dome. They are scattered through the vast and empty depths of space at vastly different distances. The constellations are not true groupings. Their stars are often light years apart from one another. Their apparent proximity a mere line of sight illusion from our singular vantage point. We know this. Our science has proven it unequivocally. And yet, we still use the model. We still teach the constellations. We still rely on right ascension and declination. This is because the model is not a failure of understanding. It is a triumph of practicality and poetry. It is a tool perfectly suited to the way we perceive the universe from our tiny platform. The sky appears as a dome. The stars appear fixed relative to each other. The patterns are there from our perspective. The model meets the universe halfway between its true, incomprehensible nature and our limited sensory experience of it. It is a bridge made of mathematics and myth, and it works. It allows us to predict, to locate, to communicate, and to explore. It is a testament to the human ability to create order from chaos, to build functional understanding, even when a complete and perfect understanding remains just beyond our grasp. This embrace of a useful model extends to our understanding of time itself, as measured by the stars. We have already discussed sidereal time, the measure of Earth's rotation relative to the fixed stars. But this creates a fascinating divergence in how we experience time. Our civil lives are governed by solar time, the 24-hour cycle from noon to noon, based on the sun's position. But because the Earth moves in its orbit around the sun, a solar day is slightly longer than a sidereal day. By the time the Earth completes one full rotation relative to the stars, a sidereal day, it has also moved a little further along its orbit, requiring an extra 4 minutes of rotation to bring the sun back to the same position in the sky, a solar day. This means that the stars rise about 4 minutes earlier each night. Over the course of a year, this adds up, causing the evening sky to change completely with the seasons. The brilliant winter constellation Orion is invisible in the summer night sky because during those months it is up during the day, washed out by the sun. This cycle is the original reason for the zodiac. The sun appears to pass through different constellations throughout the year. Our timekeeping is thus a complex negotiation between two different celestial clocks, the fixed, underlying beat of the stars, sidereal time, and the practical, daylight-driven cycle of the sun, which is solar time. The constellations provide the stable, unchanging backdrop against which this entire temporal dance is performed.
They are the constant against which change is measured, the eternal rhythm to which the faster rhythms of our days and seasons are synced. In a very real sense, the stars keep our truest time, and the constellations are the numerals on that clock.
This leads us to the most human aspect of all, the enduring power of the stories. The science of celestial coordinates has not erased the mythology, it has simply added a new, parallel layer of meaning. When an astronomer looks at the constellation Cassiopeia, they see a region of sky rich for deep sky observation, a convenient W-shaped asterism for orientation. But they also know the myth of the vain queen chained to her throne in the sky as punishment. The two understandings coexist, enriching each other. The scientific name adds precision, but the mythological name adds depth, history, and a connection to the countless generations who have looked up at the same pattern and told its story. This is why the International Astronomical Union, when formalizing the modern boundaries of the 88 constellations in 1922, did not abolish the ancient figures. They precisely defined their borders with lines of right ascension and declination, turning them from fuzzy patterns into exact parcels of celestial real estate, but they kept the ancient names. They recognized that the human need for story is as fundamental as the scientific need for data. The sky is a shared cultural heritage, a canvas for both the equations of astrophysics and the myths of humanity. To lose the stories would be to lose a part of ourselves, to sever a connection to our ancestors who used these same stars to guide their journeys, mark their seasons, and explain their world. The constellations, therefore, are more than just a coordinate system. They are a dialogue across time. They are a conversation between the ancient storyteller who saw a bear in the sky and the modern cosmologist who uses that same patch of sky to measure the curvature of the universe. It is a continuous, unbroken thread of wonder, a testament to the insatiable human desire to not only map the world, but to find our place within it, and to tell the story of what we find there. As we deepen our engagement with the night sky, we become aware that the light reaching our eyes and telescopes is more than just a measure of position or brightness. It is a complex messenger carrying encoded information about the physical conditions of its source. This information is conveyed through the subtle, precise language of spectroscopy, and unlocking it requires the absolute positional stability that the celestial coordinate system provides. Every element in the universe, hydrogen, helium, oxygen, iron, leaves its unique fingerprint on the light it emits or absorbs. When starlight passes through a spectrograph, it is spread out into a rainbow, and within that rainbow appear dark absorption lines or bright emission lines at specific wavelengths. These lines are the elemental barcodes of the cosmos. But to read this barcode for a specific star, say the red giant Aldebaran in the constellation Taurus, the telescope must be pointed with unwavering accuracy. It must hold Aldebaran's image perfectly steady on the narrow slit of the spectrograph for the duration of the exposure, which could be minutes or even hours. This is only possible because the telescope's drive system is precisely calibrated to the apparent rotation of the celestial sphere, tracking the star's motion across the sky based on its known coordinates. The constellation of Taurus provides the context, the coordinates of Aldebaran provide the exact address, and the resulting spectrum reveals the star's chemical composition, its surface temperature, its density, and even the pressure in its outer layers. This spectroscopic language allows us to understand the life cycles of stars, all from our distant vantage point. By taking spectra of countless stars across different constellations, astronomers have been able to classify them and piece together their evolutionary paths. A star's spectrum tells us if it is a youthful, hot, blue main sequence star, like Spica in Virgo, furiously fusing hydrogen in its core, It reveals if it is an aging red giant like Arcturus in Boötes, which has exhausted the hydrogen in its core and now swells to an enormous size as it fuses heavier elements. It can even identify the end stages of stellar life, the white dwarfs, Earth-sized embers of sun-like stars, or the neutron stars and black holes left behind by supernova explosions. The coordinates allow us to find and monitor these stars over years, decades, and centuries. We can watch as a star like Betelgeuse in Orion fluctuates in brightness and spectrum, hinting at the internal convulsions that will one day lead to its spectacular demise as a supernova. We can study the delicate ballet of binary star systems, where the Doppler shift of their spectral lines reveals their orbital dance around a common center of mass.
Every piece of this understanding begins with the ability to return, again and again, to the same precise point within a constellation, to gather the faint light and break it down into its constituent colors, reading the story written therein. The constellations are the quiet libraries, and the coordinates are the call numbers that lead us to the specific volumes containing the biographies of the stars. This decoding extends beyond stars to the vast, tenuous material that floats in the space between them, the interstellar medium. This medium is not empty. It is filled with clouds of gas and dust. When the light from a distant star, perhaps a blue giant in the constellation Carina, travels through an intervening cloud of cold hydrogen gas on its way to us, the specific wavelengths corresponding to hydrogen energy transitions are absorbed out of the star's continuous spectrum. The result is a dark absorption line at a precise wavelength. However, if the cloud is itself energized by the radiation from nearby hot stars, it can glow on its own, emitting light at those same specific wavelengths, creating a beautiful emission nebula like the Orion Nebula. Spectroscopy allows us to analyze this interstellar material. We can determine its composition, its temperature, its density, and its motion. By measuring the Doppler shift of these interstellar lines, we can map the motions of these giant clouds, seeing which are drifting toward us and which are receding, tracing the flows of material that will one day collapse to form new generations of stars and planets. All of this is done by pointing our telescopes at specific coordinates within these nebulous regions, often found within the boundaries of familiar constellations. The coordinates give us a handle on the seemingly formless glow, allowing us to dissect it, to understand its physics, and to appreciate its crucial role as the cosmic recycling plant, the stuff from which stars are born and to which they return their enriched material at the end of their lives. The light is the message, but the celestial map is the directory that tells us where to listen. The same celestial coordinate system that allows us to map the distant stars also provides the fundamental navigational framework for humanity's most ambitious journeys, the exploration of our own solar system. While a spacecraft's voyage to Mars or Jupiter is a feat of complex orbital mechanics, its path is still charted against the timeless backdrop of the fixed stars. The constellations, those seemingly unchanging patterns, serve as the ultimate reference frame for interplanetary navigation, a concept known as celestial navigation or astrodynamics. Before a probe like Voyager or New Horizons is launched on its grand tour, its trajectory is calculated with immense precision within an inertial reference frame, a framework that is not rotating with the Earth, but is fixed relative to the stars. Its course is plotted as a series of positions and velocities defined by the same right ascension and declination system used for the stars themselves. During its long cruise through the void, the spacecraft must know its orientation. It does this using star trackers, small telescopes that take images of the sky, identify patterns of stars, and compare them to an onboard catalog of stellar coordinates. It doesn't see Orion the Hunter. It recognizes the specific angular separations between the bright points of light of Betelgeuse, Rigel, and Bellatrix. By matching this pattern to its internal database of stellar coordinates, the spacecraft can determine its precise attitude, its roll, pitch, and yaw in space. This is essential for keeping its communication antenna pointed toward Earth and its scientific instruments pointed at their targets. The silent, distant constellations are thus active participants in our exploration, providing the fixed guideposts that keep our robotic envoys on course across millions of miles. This stellar reference frame is critically important for executing the delicate maneuvers that make planetary exploration possible. A spacecraft on its way to Saturn cannot simply point its engine and fire. It must be oriented with extreme precision to ensure the thrust changes its velocity in exactly the right direction. This orientation is determined by its attitude relative to the stars. Furthermore, when it's time to conduct a flyby of a moon like Titan, or to enter orbit around the ringed planet itself, navigators on Earth use a technique called optical navigation. They command the spacecraft's camera to take pictures of the target planet or moon against the known star field. By identifying the precise celestial coordinates of the background stars in the image and measuring the position of the planet's limb against them, engineers can calculate the spacecraft's exact position relative to its target with astonishing accuracy. This allows for last-minute, fine-tuning maneuvers to ensure the spacecraft is on the perfect path. The stars, so unimaginably distant, become the ruler against which the close-up dynamics of our solar system are measured. This technique was used to navigate the Apollo missions to the moon, with astronauts using a sextant to sight stars, and it is still used today for precision landings on Mars. The constellations provide the stable, unchanging grid upon which the ever-shifting positions of the planets are superimposed, turning the complex gravitational dance of the solar system into a solvable problem of geometry and motion. This reliance on the celestial sphere extends to the very way we measure time for these missions. Spacecraft operations use coordinated universal time for planning, but for precise orbital calculations, they often use ephemeris time, which is based on the orbital motion of the planets, or they reference sidereal time. Tracking stations around the world must know exactly where to point their massive antennas to communicate with a distant spacecraft. The position of that spacecraft is given in its celestial coordinates, and the position of the tracking station on the rotating Earth is known in geographic coordinates. To calculate the correct pointing angle for the antenna, engineers must account for the Earth's rotation, and this is done using sidereal time, the measure of time based on the Earth's rotation relative to the vernal equinox, the fundamental starting point for the celestial coordinate system. The entire global network of deep space communication, the Deep Space Network, is thus synchronized not just to the clock on the wall, but to the apparent motion of the stars. The slow, steady turning of the celestial sphere dictates when a tracking station in California, Australia, or Spain will have a view of a particular spacecraft, its position calculated against the fixed stars. In this way, the constellations are more than a map. They are the metronome that keeps the symphony of interplanetary exploration in time, a constant, silent pulse that guides our machines and our ambitions as we take our first tentative steps out into the cosmic ocean, always using the ancient lights as our surest guide. In our serene journey through the cosmos, guided by the fixed patterns of the constellations, we have so far operated under the comforting assumption of a stable and rigid stage. Yet the universe, in its deepest nature, is not rigid. Albert Einstein's theory of general relativity revealed that space and time are woven together into a single fabric called space-time, and that this fabric is curved and warped by the presence of mass and energy. This curvature is what we experience as gravity. This profound truth means that our celestial coordinate system, for all its precision, is not drawn on a flat, static canvas. It is mapped onto a dynamic, malleable medium that can stretch, compress, and bend. The paths of the very photons that carry starlight to our telescopes are not perfectly straight lines. They are geodesics, the shortest paths through curved spacetime. This means that a star's apparent position, as recorded by its celestial coordinates, is not its true position. The light from that star has been subtly deflected on its journey to us by the gravitational influence of every massive object it has passed. The most dramatic example of this is gravitational lensing, where the gravity of a massive galaxy cluster can bend the light from a more distant galaxy, distorting its image into spectacular arcs or even multiple images. To understand the true nature of the lensed object, astronomers must first understand the distortion of the lens itself, a process that relies on knowing the precise, undistorted coordinates of the background sky against which the lensing occurs. The constellations and the coordinate grid they define provide that fundamental, undistorted reference frame, the baseline from which all warping is measured. This relativistic bending of light is not just a dramatic effect for distant galaxies. It is a constant, subtle factor that must be accounted for in all high-precision astronomy. Even within our own solar system, the sun's gravity acts as a lens, very slightly shifting the apparent positions of stars that lie near it in the sky. This effect, predicted by Einstein and famously confirmed during a solar eclipse in 1919 by observing stars in the constellation Taurus, was a pivotal proof of general relativity. Today, for any observation that requires extreme astrometric precision, such as measuring the minuscule parallax shifts of stars for the Gaia mission, scientists must apply complex models to correct for the gravitational deflection caused by the sun, the planets, and even large asteroids. The light from a star in, say, the constellation Lyra does not travel a perfectly straight line to us. Its path is minutely bent as it passes by the sun. To know the star's true position, we must calculate and remove this deflection. The constellations, therefore, represent the ideal, unperturbed positions. The work of the modern astrometrist is to measure the difference between where we see the star and where the celestial coordinate grid says it should be. And in that difference, they find the fingerprint of mass, warping the fabric of the universe itself. The map is not just a tool for finding things. It is a tool for measuring the very distortions of the stage upon which the cosmic drama plays out. This concept extends to the flow of time itself, a phenomenon known as gravitational time dilation. According to general relativity, time runs slower in stronger gravitational fields. A clock on the surface of the Earth ticks very slightly slower than a clock on a GPS satellite in a higher, weaker orbit. For the global positioning system to provide accurate locations, the satellites must constantly correct their onboard atomic clocks for this effect, as well as for the velocity-based time dilation from special relativity. If they did not, the system would accumulate errors of several miles within a single day. This correction is calculated based on the satellite's precise positions in their orbits. And how are those orbits defined and measured? They are tracked against the celestial reference frame. The satellites and the ground stations that monitor them use the fixed positions of quasars, the most distant and stable objects in the universe, to define the orientation of the Earth in space. This incredible chain of reasoning connects the everyday act of using a map on your phone to the most esoteric laws of physics. Your location is determined by satellites whose clocks are adjusted for Einsteinian time dilation, whose orbits are measured against a background of galaxies billions of light years away, a background organized into a coordinate system that we still, poetically, link to the ancient constellations. The myths of the heroes and beasts in the sky have, through the long, patient accumulation of human knowledge, become intimately woven into the fundamental fabric of space-time, providing the stable ground against which we can measure even its most subtle and wondrous warps. In the quiet vastness of the cosmos, where distances are so immense that even light takes millions of years to bridge them, the question of communication arises, not just between humans and their machines, but as a profound philosophical pursuit. If we are not alone, how would we ever find others, or they find us? And if such a momentous encounter were to occur, what language could we possibly share? The answer, perhaps, lies in the one universal constant that any technological civilization would inevitably discover: the map of the sky. The celestial coordinate system, based on the apparent positions of pulsars and the fundamental plane of our galaxy, represents a potential lingua franca for the cosmos, a Rosetta Stone etched in light and time. This is not mere speculation. It is the principle behind the message carried on the Pioneer plaques and the Voyager golden records. These artifacts, destined to drift between the stars for eons, contain maps pointing back to our solar system. But they do not use human languages or arbitrary symbols. They use the only truly universal language we know: the language of astronomy. The Pioneer plaque, for instance, uses a pattern of lines to represent the positions of 14 pulsars relative to our Sun. Pulsars are the spinning corpses of massive stars, emitting beams of radiation that sweep across space with the precise regularity of atomic clocks. Each pulsar has a unique signature, its pulse period. The plaque provides these periods in binary code, using the hyperfine transition of hydrogen, the most common element in the universe, as a universal unit of time and length. Any civilization that understands the basics of physics and astronomy could, in theory, decode this map. They would recognize the pattern of pulsars, note their unique periods, and triangulate the location of the star system from which the plaque was launched: our Sun. The map is not based on our constellations, but on a deeper, more fundamental cosmic geography that any observer would eventually chart. This concept of a celestial map as a universal address finds a haunting and beautiful echo in the scientific search for extraterrestrial intelligence, known as SETI. For decades, astronomers have used radio telescopes to scan the heavens, listening for a signal that is clearly artificial, a beacon in the cosmic noise. But the sky is immense, and scanning every frequency and every point is an impossible task. So, where does one point the dish? SETI researchers often use a strategy of targeted search, focusing on stars that are sun-like and older, providing enough time for technological life to arise. And how are these target stars identified and communicated to the telescopes? By their celestial coordinates. The constellation provides the human-readable context, while the coordinates provide the machine-readable instruction for pointing. But there is a deeper layer to the strategy. Some scientists propose that a truly advanced civilization might use the most obvious and stable landmarks in the galaxy for their broadcasts: the center of the galaxy, or the plane of the ecliptic, or even the specific frequencies associated with universal elements like hydrogen or hydroxyl. These are the constants that any civilization would discover. In this sense, the entire SETI endeavor is a testament to the belief that the laws of physics and the geography of the galaxy are a shared knowledge, a common ground from which a first conversation could begin. We are, in effect, listening to the constellations, hoping that amidst the natural symphony of pulsars and quasars, there might be a single, deliberate note of greeting, timed to a rhythm we can understand, and broadcast from a point on the map that we have all learned to read. This pursuit leads to a humbling and poignant realization about our own place in the cosmos. The coordinates we use, the constellations we see, are from a single perspective. A civilization orbiting a star in the Andromeda galaxy would have a completely different night sky. Their celestial pole would be elsewhere. The constellations would be their own. Their coordinate system would be just as valid as ours, but it would be built from their unique vantage point. This means that any message we might receive, or any message we might send, would have to be translated from their cosmic address to ours. It would require a shared understanding of the absolute markers of the galaxy, the rotational center, the positions of uniquely identifiable objects like supernova remnants or micromaser emissions, or the precise timing of pulsars. The constellations of Earth are our local map, our personal chapter in a much larger story. To communicate beyond our celestial neighborhood, we must learn to use the galactic index to reference the landmarks that are visible from anywhere in the local group. This is the ultimate purpose of our precise celestial cartography. It is the first step in learning to see the universe not just from our perspective, but from any perspective. It is the foundation for a potential future where we might not only be charters of the cosmos, but also participants in a galactic community, using the silent, steady language of mathematics and physics written in the immutable positions of the stars to finally break the silence and find our kin amongst the light. As we extend our gaze from the immediate present to the far future of the cosmos, a profound and sobering reality emerges. The celestial map we have labored for millennia to create is not eternal. The universe is dynamic and evolving on the grandest scales, driven by forces that will, over almost incomprehensible spans of time, fundamentally alter the sky until it is unrecognizable. The primary architect of this change is the continued acceleration of the universe's expansion, fueled by the mysterious presence of dark energy. As space itself stretches at an ever-increasing rate, the cosmos beyond our immediate gravitational family will begin to vanish from view. Galaxies that are currently visible will have their light stretched into longer and longer wavelengths, first shifting from visible light to infrared, then to microwaves, and eventually their photons will become so redshifted and diluted that their energy will be indistinguishable from the background noise of space. Their distances will increase beyond our cosmic event horizon, the point beyond which light can no longer ever reach us. The constellations, which today are filled with the faint smudges of distant galaxies, will slowly empty of these external island universes. The night sky will become not just dark, but profoundly isolated. The great galaxies of Virgo and Coma Berenices will fade away, leaving behind only the faint, ancient glow of the cosmic microwave background, itself redshifted into ever fainter and longer wavelengths. The map will lose its deepest layers, its farthest reaches, becoming a local map of only the most gravitationally bound objects. This isolation will be accompanied by a great stellar fading. Stars themselves have life cycles, and the future of the universe is one of increasing darkness as stars exhaust their nuclear fuel. The massive, brilliant blue stars that outline many of our constellations have short lives, measured in mere millions of years.
They will be the first to disappear, exploding as supernovae and leaving behind neutron stars or black holes. Sun-like stars, such as our own, will last for billions more years before swelling into red giants and then collapsing into white dwarfs, eventually cooling into cold, black cinders over trillions of years. The last stars to shine will be the faint red dwarf stars, which burn their hydrogen fuel so slowly that they can shine for trillions of years. But even their energy is finite. The universe will eventually become a place of darkness, populated by the degenerate remnants of stars, white dwarfs, neutron stars, and black holes, drifting apart in the ever-expanding void. The familiar patterns of the constellations, Orion, Ursa Major, Scorpius, will be utterly erased. The stars that compose them will have died, moved, or faded into invisibility. The celestial coordinate system, so carefully built on the positions of these stars, will become obsolete, its reference points gone. The sky will offer no familiar landmarks, no stable grid. It will be a black expanse, punctuated only by the rare, faint glow of a failed star or the distant, unseen tug of a black hole.
the great clock of the cosmos will have run down, and its face will be blank. In this context, our current epoch is a moment of breathtaking privilege. We live in the stellar era, a golden age of light when the universe is still young enough to be filled with shining stars and bright galaxies, yet old enough for us to have evolved to see them. We exist in a narrow window of cosmic time where the sky is both navigable and meaningful, filled with patterns we can name and mysteries we can strive to solve. The precise celestial coordinates we use today are a product of this unique era. They are a snapshot of the sky as it appears at this specific moment in the 13.8 billion year history of the universe. This lends a deep poignancy to our astronomical endeavors. The star catalogs we are compiling, the exoplanets we are discovering, the deep field images we are capturing, they are not just for us. In a very real sense, we are creating a permanent record of the universe in its vibrant youth. We are mapping a sky that will not last forever. Long after the last star has faded and the constellations have dissolved into history, the data we gather now could remain, a fossilized memory of a brilliant, structured, and knowable cosmos, a testament to a species that, for a brief moment in the vastness of time, looked up, recognized the patterns, and, with patience and wonder, learned to read the map of the heavens. Our work is a message in a bottle, not just across space, but across time, preserving the beauty of the transient stellar era for whatever or whoever may come after, in the long, dark night that awaits the universe. Amidst the grand scales of cosmic time and the precise language of coordinates, it is essential to return to the most fundamental truth of our relationship with the night sky. It is a source of pure, untethered wonder. Before a star is a data point with a right ascension and declination, before a constellation is a defined region of a catalog, it is a spark of light that has captivated the human heart for millennia. This sense of awe is not diminished by scientific understanding, it is enhanced by it. Knowing that the faint smudge of the Andromeda galaxy is 1 trillion suns whose light has been traveling for 2.5 million years to reach your eye, transforms a casual glance into a profound connection across time and space. Understanding that the red glow of Betelgeuse is the feverish radiance of a dying supergiant, a star so vast it could engulf the orbit of Mars, adds a layer of dramatic poignancy to the pattern of Orion. The scientific facts do not replace the mystery, they deepen it. They provide a new vocabulary for our awe, a new set of stories that are every bit as compelling as the ancient myths. The constellation becomes a portal, and the coordinates are the key that unlock a deeper narrative, one written in the laws of physics and the poetry of stellar evolution. This fusion of knowledge and wonder is the true heart of astronomy, a discipline that satisfies the intellect without ever extinguishing the primal spark of curiosity that first made us look up. This personal connection is beautifully embodied in the simple, timeless act of stargazing itself. To go outside on a clear night, away from the glare of artificial lights, and to simply look up is to participate in the most ancient of human traditions. It requires no technology, no special knowledge. It begins with the simple recognition of a pattern. There is the Big Dipper. From that anchor point, the sky begins to organize itself. You can use the pointer stars to find Polaris, the North Star. You can follow the arc of the Dipper's handle to Arcturus in the constellation Boötes, and then speed on to Spica in Virgo. This star hopping is the human-scale application of celestial coordinates. You are using the bright, familiar landmarks to navigate to fainter, more distant ones. With each new star or constellation identified, the map in your mind expands. The sky transforms from an overwhelming chaos of lights into a familiar landscape, a place where you can find your way. This process is deeply meditative. The slow, patient scanning of the heavens, the gradual acquisition of the sky's geography forces a quieting of the mind and a focusing of attention. The concerns of the earthly world shrink under the immense, silent grandeur of the cosmos. It is an experience of humility and perspective, a gentle reminder that we are part of something vastly larger than ourselves. The constellations are the guides on this personal journey, the friendly faces in the cosmic crowd that welcome you and show you around their stellar neighborhood. In our modern, hyper-connected world, this personal, quiet engagement with the night sky has become a rare and precious form of mindfulness. It is an antidote to the constant noise and stimulation of daily life. There is no notification, no update, no message that can compete with the steady, silent drift of the stars as the Earth turns. Learning the constellations is not about memorizing facts. It is about building a relationship with the cosmos. It is about the quiet satisfaction of being able to step outside and know, without any digital assistance, that the bright object hovering in the twilight is Venus, or that the faint, hazy patch visible with averted vision is the Pleiades star cluster. This knowledge is a form of cosmic literacy, a way of reading the oldest book in existence. It forges a direct, personal link between you and the universe, a connection that is both intellectual and emotional. The celestial coordinate system is the formal, scientific expression of the sky's order, but the constellations are its poetry. They are the mnemonic devices that allow that order to live not just in databases and textbooks, but in the minds and hearts of people. They ensure that the map of the universe is not just a tool for experts, but an inheritance for everyone, a shared treasure of beauty and wonder that continues to inspire, comfort, and humble us night after night, season after season, generation after generation. And so we arrive at the end of our contemplation, having journeyed from the instinctual patterns seen by our ancestors to the edge of the observable universe and the far future of cosmic darkness. We have seen how the simple, beautiful act of connecting stars into pictures laid the foundation for a precise, mathematical grid that guides our telescopes, our spacecraft, and our understanding of physical law. We have explored how it allows us to measure the distances to stars, the structure of our galaxy, and the expansion of space itself. We've considered how it must account for the subtle warping of space-time and how it might one day serve as a universal language for communication beyond our world. This journey reveals a profound truth. The story of celestial coordinates is, in its entirety, the story of human curiosity itself. It is a narrative that stretches back to the first person who looked up and wondered, and forward to the most advanced speculations of cosmological theory. It is a continuous thread connecting the mythic imagination of the past with the data-driven exploration of the present, demonstrating that these two ways of knowing are not in opposition, but are instead complementary strands of the same enduring quest to find our place in the cosmos. The constellations and the coordinate grid they support represent a perfect harmony between poetry and precision. The myths provide the soul, the stories, the cultural memory, the human connection to the sky that transcends generations. They are the reason we care to look up in the first place. The coordinates provide the intellect, the tools, the measurements, the predictive power that allows us to test our ideas and expand our knowledge. One without the other is incomplete. A sky understood only through numbers is a sterile and distant place. A sky understood only through stories is a beautiful mystery, but one that remains
ultimately unknowable. Together, they create a rich, layered understanding that satisfies our need for both wonder and comprehension. They allow us to appreciate the brilliant red of Antares in Scorpius, both as the heart of a celestial scorpion and as a dying supergiant star hundreds of light years away, whose immense size and evolved state are written in the specific spectral lines of its light. This dual vision is astronomy's greatest gift. It allows us to see the universe with both our hearts and our minds, to feel the awe without sacrificing the understanding. As our journey concludes, we return to where we began, under a vast, dark sky, looking up. The knowledge we have gathered does not shrink the cosmos. It expands our ability to appreciate its grandeur. The stars are no longer just points of light. They are distant suns, each with its own story of birth, life, and eventual death. The constellations are no longer just pictures. They are ancient landmarks, chapters in a cosmic map, and the starting points for unimaginable journeys of discovery. The silence of the night is no longer empty. It is filled with the faint whispers of photons that have traveled for millennia to reach us, carrying encoded messages about the composition of stars, the presence of planets, and the history of everything. To learn this language, to become literate in the map of the heavens, is to transform the night sky from a passive backdrop into an active, engaging, and deeply familiar landscape. It is to never feel truly lost, for you can always look up and find your bearings in the turning of the stars. It is to carry with you, always, a quiet sense of connection to the universe, a connection built on wonder, refined by knowledge, and sustained by the enduring, peaceful beauty of the starry vault above. So, let the constellations be your guide. Let their steady light be a comfort. And may your own place in the cosmos, however small it may seem, always feel connected to the infinite, the eternal, and the profoundly beautiful dance of the heavens. Good night, stargazer. We will meet again in our next exploration.